In this video, we're going to take a look at an example of integration by parts with repeated integration, or a repeated integration by parts example. And how do we know, how can we tell that that's going to happen? Well, if we look at our integral, once again we have a polynomial times an exponential, no way to simplify that. And if we use e to the x with x as our u to do u substitution, again we're not going to get an x squared out of that, so we can't get rid of the x squared. Now if you notice what happens each time we do this integration, or when we do this integration by parts, the reason why it works is because we're going to differentiate the x squared, or we're going to differentiate the polynomial function, and when we do that we reduce it in degree by 1. Now in the past we've worked with examples where we always had a first degree, so in that case it resolved down to just a constant. This time we're going to get it to resolve to x, and then from x down to 1, so we have to do this 2 times. So let's take a look at what this how this will go. Alright, I'm just going to jump in with our u and our dv. We have u equals x squared and dv equals e to the x dx. Taking the differential of u, we get du is equal to 2x dx, and the integral of dv is going to be just e to the x. So I can put it together. Then we have integral x squared e to the x dx is equal to uv, which is x squared e to the x, and then integral v du, which is going to be 2x e to the x, and I'll bring the 2 out. And so you can see we've simplified it, but we still have an integral that cannot be antidifferentiated by any other method right now. So we're going to have to use a repeated integration by parts here. And we're going to let u equals x and dv equal e to the x. We shouldn't worry about using u and dv again. We use them and they're gone. So they're available for reuse again. There's nothing of u and v from the previous instance still around. So it's okay. Don't worry about using them again. Differentiating u, this time we get du equals dx, and the integral of dv is still e to the x. So we put it together again. So we have x e to the x minus 2 times, now this time integral x e to the x dx is another uv, which here is x e to the x minus the integral of e to the x dx. And at that point we have an integral that can be evaluated. You just have to be careful with applying all the negatives and the constants, distributing the constants out. So first of all we get x e to the x minus 2x e to the x, and then we have minus a negative, so it's going to be plus the integral of e to the x, which is just e to the x, but we have to multiply that by 2, and so it's going to be 2e to the x. So to simplify this a bit, and we should add a plus c at the end of that, and to simplify we can factor out an e to the x. And sorry, I just noticed that in the first term I should have had x squared there all along. So when I factor out the e to the x, I'm going to be left with an x squared, and that brings us to the end of that. So this is an example of the repeated integration by parts, and that's going to be the end of that video.